What was that last bug that was really easy to fix, but difficult to find? And what made it so difficult to find? My generalized theory? Lack of access to crucial information. Let me explain. To my mind, our applications are huge, complicated factories with its inputs and its outputs. And even when we are trying to understand them, we are sitting on the outside, looking in. Specifically, we commonly have 3 tools at our disposal. Number 1, reading the source code. Sadly, the source code is only a static blueprint of the actual thing that is running in the real world. We place fax machines in specific locations around the factory in form of console log and or printf statements. These fax machines gather data. We can then use that data to better understand the control flow and data flow of our applications. Some developers use a third tool, the traditional debugger. Using the traditional debugger is like taking a flashlight and a magnifying glass and then going into the factory, which by the way is pitch black. There's no lights, and trying to find that bug that is hidden somewhere in the corner. Despite all their shortcomings, these are the 3 most commonly used tools for debugging. Of course, there are more tools, such as the browser development tools, but they are more domain-specific, not general purpose. So what is that metaphorical factory that we are trying so desperately to understand? It is the dynamic runtime behavior of our applications. And I also consider it the dark matter of debugging because it is almost invisible and intangible to us as developers. We can barely see it, we can barely interact with it, it is elusive. This is where the developer's most valuable skill comes into play, our ability to establish mental models of these invisible, complex, high-dimensional space that is the dynamic runtime behavior of our applications. These mental models are inherently difficult to establish, and it is our goal to help the developers in exactly this process by illuminating the dynamic runtime behavior, making it more visual and more interactive. This is of course not a new idea. In 1997, MIT's Andrew Lieberman already proposed developing better tools to help programmers with this most difficult aspect of their jobs. Too bad that 25 years later little progress has been made toward that goal. But this is where we come in. How do we make our dynamic runtime behavior more visible and more interactive? And one possible answer to that is Debuggers, an omniscient debugger and integrated debugging environment for JavaScript. Before we take a look at Debuggers, shout out to Replay.io, they are also trying to answer the same question. Debuggers comes with 5 different toolsets that help the developer analyze and investigate their runtime behavior. You can use the timestamps below to skip ahead and look at the tools that you are most interested in. Let's start with maps, specifically the call graph. We also call it the synchronous call graph in order to distinguish it from its asynchronous counterpart that we will look at later. Let's start with this nice and simple example. First, we run it with debugs enabled. Then we can close all this down and open the call graph. Now we can investigate the call graph any which way we like. We can show everything at once, or just investigate one node at a time. If we open this up, we can see that F executed twice, and G executed 4 times. The call graph also captures the caller-callee relationship. This way we can see that these 2 executions of G were called from within this execution of F, and these 2 executions of G were called from this execution of F. If a file or function was executed on an empty stack, meaning it does not have a caller, it becomes a call graph root. And the roots of the call graph are exactly these 3. For example, we have our entry point, the file, callgraph1.js, and we also have these 2 callbacks over here to set timeout, which were executed by the JavaScript engine on an empty stack. And we find these 2 over here. A total of 3 call graph roots. The call graph might feel intuitive, because it is one of the most fundamental data structures to represent the overall control flow of our applications. The call graph is basically the call stack evolved over time. For example, when G executed, the call stack was G, F, and then the entry point, callgraph1.js. The execution of an application is the equivalent of the DFS traversal of the call graph. We can show or hide all kinds of details, such as the location of the function that executed, or the values of the arguments and return value of each function. We can also show or hide all kinds of stats, such as the amount of modules involved in the subgraph, the amount of files involved in the subgraph, the amounts of files and function executions in the subgraph, as well as the size of the trace log, and so on. Let's have a look at another example. Computer scientists love to use the Fibonacci sequence to introduce the concept of recursion. Let's have a look. The entire graph looks a little like this. Let's remove some clutter. And let's have a look at the inputs and outputs of every call to the Fibonacci function. we can see that the 6th Fibonacci number is 8, the 5th is 5, the 4th is 3, and so on. We can also see how number 1 and number 2 become number 3, and then how number 3 and number 2 become number 4, and so on, and so on, and so on, and so on. No more need to manually draw up your recursion trees. Let's have a look at a simple real-world example. This is a simple to-do list front-end application. This is its entry point. And this is its call graph. What does a to-do list application do? It organizes a to-do list, such as this one. These are all the call graph routes involved in initializing everything. We see several files involved in the application, and we can see that most of the work happened in app.js as well as the setView function over here. Clicking it takes us right to it. We can see from this line over here that the setView function is probably an event handler of the load event. What else can we see? If we look at app.js, it looks quite convoluted, but we can remove some clutter, and we can see only the function names involved in this call graph. Most of the functions involved seem to be the on function, which, if we click it, takes us there, and we can see that it is just a function that wraps the addEventListener function, meaning that all of app.js seems to be responsible for registering a lot of event listeners. Most of the work done during initialization was done in app.js, but a lot of the work was also done in the setView function. So what is the setView function? We can open it up, look at individual children one at a time, and we can quickly see that the re-render function appears, which also seems to be doing most of the work here, leading us to believe that this is where most of the rendering logic happened. Following this train of thought, we can now inspect the re-render function to understand what actually happened during rendering. Naturally, looking at the subgraph of this function should reveal a lot about what happened during rendering. We open the whole thing, and we can see that, again, things are a little bit convoluted. It takes some getting used to working with the call graph to better determine when to hide things and when to show things. In this case, the re-render function calls the store.find function, which probably gets us all the to-do items. Let's click there, have a look. Find gets us, indeed, all kinds of to-do items. Can close that down. We look at the next thing over, which is then the show items function, which seems to be rendering everything into some sort of HTML string, a string that is being compiled, apparently, in the item list function. If we look over here, show items indeed has one child of item list. We look at that, and here it is. Here's the logic that compiles the HTML string. Let us look at two more use cases of the call graph. Close all of this down. And we quickly look at this, and this is only the initialization. Now, our application is still live. We can now start interacting with the application and quickly identify how the call graph evolves while we interact with the application. For example, let's click one of the to-do items, such as this. I only clicked it once. Now I go back to the call graph, and I see that 3 new nodes have appeared. In fact, the same function was called 3 times. Let's look at it. Number 1. Number 2, number 3. To no surprise, we always end up in the exact same location, this patch event function. We can further investigate and see that a toggle item function is being called over here, which in turn calls render yet again. We have seen render before during initialization. Let's have a look over here. Let's open that up, have a look at this, and there again, there is re-render, the re-render function here and here. And we can see that the amount of work that was being done is less than initially. We can now even compare the two render calls. Again, this is the initial render call, and this is re-rendering after we have toggled an item by clicking into it. Sometimes it can be very useful to compare two subgraphs with one another. Let's open this up, and we can see the difference in the two subgraphs. Most importantly, these two functions were called initially, but they were not called during re-rendering, while the other 5 functions that have been called from within the re-render function here have also been called over here. Of course, reading these call graphs is no easy feat. It requires some practice, it requires getting used to, it requires some experience, But it also enhanced our ability to establish the call graph in our own minds when there was no tools available. This call graph is great for understanding synchronous control flow. But when things turn asynchronous, another kind of tool is needed. Enter the asynchronous call graph to help you when things get complicated. The asynchronous call graph is our own little invention, designed to automatically capture all asynchronous control flow in our applications. For example, let's have another look at our to-do list. This is the to-do list initially. Now, as I interact with it, I click here, I click here, I click over there, maybe I click over there, maybe I'll enter a new to-do item. I press enter. When I do all these things, JavaScript code gets executed. We can see that in our synchronous call graph. If you remember, the top here was the call graph of the initialization of the application. And then down below, we have all kinds of event handlers. They all represent some code that executed as a result of me interacting with the application, such as clicking it, clicking it, clicking it, clicking it, and then here entering a new to-do item. But in this call graph, I only see a singular timeline of all the events. That does not help me a lot if I try to understand what the relationship between the different events is. That is where the asynchronous call graph comes into play. We can switch to it using this button. Here we only see the call graph roots, only the code that was executed on an empty stack, such as the imported files, our entry point app.js, our onload view handler, and also, as we see on the right, all the event handlers. The asynchronous call graph groups all executions of the same event handler into a singular column. So how could we find out which column corresponds to which event handler? One way is to go to the dispatch event function, look at the code, find an expression that holds relevant data, such as the selector, select it, and then enable the value button. We now see the value of the selector during each execution of this event handler. Nothing is shown over here because during the execution of this event handler, this function did not execute. If we click into it, we can see that this is the change event handler, which is handled very differently. Let's go back and add a few more items. Here we go. Gonna add to do 5, enter, to do 6, enter, and we go back to the asynchronous call graph. As you can see, more nodes have been added in this change event handler column. Let's select a more meaningful value, like the title. Select that, and we can see to do 4, to do 5, to do 6. These are the call graph routes responsible for adding each one of these items. This helps us make sense of the high-level asynchronous control flow of our application. If we were now interested in the individual things that happened during handling each of these events, we can just click any one of these, such as this one, and then switch back to the synchronous call graph over here. As you can see over here, the corresponding call graph route is still selected over here. We can re-enable our stats because we have more space to display them here. And we can see that there's a lot of work that was done inside of this call graph route. We can now expand it, and we can see all the function calls involved in handling this event. We find that this really helps us better understand the different aspects of our applications and how they're interrelated. But the asynchronous call graph can do so much more. Let's have a look at some more examples. This little sample application has a lot of awaits, asyncs, and promises. Looking at the synchronous call graph, we only see the different parts of our execution on a singular vertical timeline. The asynchronous call graph makes a lot more sense. For example, we see the 3 awaits in our main function, 1, 2, and 3. Over here, 1, 2, and 3. And can now relate the execution of main to the execution of all the other functions that are participating in this big mess. Here we can see the concurrency that happens in our applications, such as F1 and F2 executing serially, but concurrent with G1 and G2, concurrent with H1 and H2. Being aware of this concurrency can help us identify and deal with potential race conditions. For the fun of it, let's have a look at sequelize, the famous JavaScript SQL or SQL library. We just executed this code, and it failed. Let's focus on the main things that are happening. We are creating a model. We are awaiting initialization of sequelize via its sync function. Then we run 2 queries in parallel, user find or create here, and then another user find or create over here. This will fail, as indicated by the flame icon, which brings us to the catch statement down here. Let's look at the call graph. A lot of things are happening. Let's look at the async call graph. First, let's disable all detail. And now we can select the sync function over here. And we can see that the sync function started in this first node. Now we can select await. And we can see that the end of the initialization is down here. Now we can zoom out just a little bit. And now we can already see that initialization went all the way from over up here to all the way down here. If we turn detail back on, we can get a sense of all the things that happened during initialization. Initialization is followed by the two find or create statements over here, which then split off, one over here and one over here. Finally, we come to console.error down here. Select that, and you might think that is the end of it. But as the asynchronous call graph reveals, this is not it. More things are happening down here that you might not be aware of because of a fallacy of promise.all, which we might discuss in some other video. So what have we learned? We have learned that asynchronous code can be very complicated, that sequelize initialization involves all this code, that the two find or create queries are splitting off over here, 1 and 2, and that the end of the main function is not always the end of our program. If you are interested, here are 3 more examples of JavaScript code and their corresponding asynchronous call graphs. Our last type of map is the asynchronous call stack, an individual slice of the asynchronous call graph frozen at one point in time. For example, let's go back to the sequelize call graph. The flame icon over here indicates that an error was thrown during the execution of this call graph route. Let's click it. The error was thrown over here in this line. Let's open up the asynchronous call stack to better understand how we got here. Let's make it bigger, enable code locations, and compare it to the call stack that was reported by Node itself. The reported call stack looks like this. As you can see, this is a problem because it does not include all the asynchronous call graph routes that precede it. Inability to deal with asynchronous transitions is an old problem of JavaScript and has been frequently discussed in the community. The biggest problem is that it does not tell us which sequelize function we called that caused the problem. Our asynchronous call stack clearly indicates that it was this call right here. If we click it, it takes us right to it. Let's move on. Next, we have some very basic global investigation tools. Let's look at the sequelize example one more time. The sequelize application has already executed. Our entry point is over here. And over here in our debugs view, we can find the global view. If we click it, we can see an overview over all errors, all console logging, console log, console warn, console error, console debug, all of them, as well as all recorded packages, all recorded import and require statements, and search results that we will discuss later. For example, if we look at the errors, we open them up, we click the first one, and it takes us here, and we can see it's inside of some UUID library, and it's being caught and not being dealt with. Maybe more interestingly, if we go down here to the fourth one, we see the error we looked at earlier. Furthermore, we have the console log statements over here, which for sequelize generously log the database transactions, followed by the recorded packages. We have a total of 404 files. This includes our own application as one package, as well as any package in Node modules. Any one of these entries is clickable and takes us exactly to its location in the code. But wait, there's more. To better understand things on the lowest level, we have local investigation tools. For example, let's find out how our to-do list gets rendered. We see 4 to-do items, 1, 2, 3, 4. How do we make them appear? Let's try to answer that question. From the call graph, we can quickly find the re-render function. We can now, on the left, use the trace details menu to investigate the function. First, we select a piece of code that we find particularly interesting, such as, for example, here, the data that we are trying to render. We place the keyboard cursor on it and then use this red button to select it, which also is over here, and then start our investigation. For example, we can investigate the value. We click this and can see that data is an array with 4 entries. 1 is to do 1, to do 4, to do 5, to do 6. This is the data that is being rendered. This way we can investigate any data. We can also navigate. Just like the traditional debugger, we have our step over, step into, and step out buttons. However, unlike the traditional debugger, we can step in both directions. We can now move forward to the show items function down below to understand how the actual rendering is happening. We can now step into, which brings us right to the show items function. As you can also see on the right, the call graph moved with us. Here we can see that the HTML is being produced by another function called item list. We can also step into that one. item list calls reduce in order to produce a single string from the 4 items that we saw. Again, we can just select any value that we want to investigate it. For example, we can click the title over here, investigate that, and we can see that the value is TODO1 in this execution. However, this whole thing executed 4 times. And under executions, we can see all 4 executions and the value that it contained. We can also click any of these to take us to the exact point in time that this execution occurred. As you can see on the right, the call graph again follows us wherever we go. This concludes our overview over trace details with its navigation, value inspection, and executions. Next up, data flow tools. These tools allow us answering exactly these kinds of questions. They might sound familiar. For example, in our to-do list, we might be interested to better understand where our to-do items are coming from exactly. Looking back at the code, we see that the item list function is responsible for producing a single HTML string from the items array. But where are items coming from? Let's select the items. And now on the left in the data flow view, we can see all the places where items were accessed or assigned. Clicking through this list takes us to all these different places. The first entry in this list is generally the one where this value was created. Like in this case, filter created a new array that we saw in the render function. If on the other hand we select an individual item, like this, we see that the result is somewhat different. We can find out where each individual item was created. For example, this item was created over here from JSON parse of some string that was stored in local storage. We can also filter this list by access or by assignment. By default, we track the data flow of values. For example, if I select Y, which has the value 1, we find all the places where this particular one occurred. Here, 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 and here. But we can also track variables. If we again select Y, switch to the variable selector, we can see only the places where Y was read or written to. This allows us answering these questions. Now let's move on to the last part. Dbux has specialized search tools that only operate on runtime data. In our last example, we are playing with the popular Express library, which is commonly being used as a web server on Node.js. We are looking at one particular Mocha test case that we just executed with debugs enabled. Down below in the terminal, we can see the results. Suffice it to say, things did not go well. Let's find out why. We have multiple options. We can either search by executed files or functions, which we call contexts. We can search by individual pieces of code, which we call traces. Or, most fun of all, we can search by value. So what went wrong? Let's look at it. The expected value was get, put. However, the actual value was get, put, get. Meaning that get, put, get is the wrong result that was created. If we can find out where it came from, we can probably find the culprit. So let's search by value. Get, put, get. Enter. All corresponding call graph nodes that contain the value are now highlighted on this side. And over here, we can see all the search results, currently sorted by file and function name, and then furthermore by value. These are all the places where get, put, get appeared. In all likelihood, we are looking for the first place where it appeared. So let's just click the first one, that one over here, and this is it. This expression has the value get, put, get. We can verify by looking at trace details and checking out the value down here. Get, put, get. Also, this line of code only executed exactly once. In all likelihood, this is our culprit. And as it turns out, it is. The string is produced from the options array, which we can also select by first placing the cursor on it, pressing the red button, and then looking at it over here. Get, put, and get. And if we're interested, we can further trace down where options came from by, for example, looking at data flow and finding all the places where it was modified. But as it turns out, that will not be necessary because the bug is in fact right here. This concludes the first introduction of the search function. Last but not least, we might want to touch on some disadvantages of debugs. And the answer is yes, there are some, as you can see here. For more detailed explanations and documentation, check out our website. All the links are in the video description down below. I hope you have the time to check it out and give us any feedback, any complaints, anything whatsoever, you let us know. Thank you.